Hi, my name is James McDonald, Technical Advisor for F.A.S.T Virtuwell at F.A.S.T. Virtuwell is a production optimization tool which can be used to gain a better understanding about what is happening throughout the entire flow path within your wellbore. Whether you are modeling actual wells or creating theoretical cases, using Virtuwell you will gain confidence in determining optimal operating conditions. In Virtuwell we would begin by selecting the type of wellbore we need to build from either a vertical wellbore, a simplified horizontal wellbore where we can specify a kickoff point, a heel, and a toe and assume the entire horizontal portion of the wellbore is equally contributing to the overall production of the well, or a general wellbore where the degree of inclination of your wellbore is determined by the difference of the inputted measured depth and true vertical depths for each segment. The general wellbore also allows the user to input as many separate productive intervals as desired. After we have selected and entered our fluid properties, we would be ready to go ahead and begin using one or multiple modules within the F.A.S.T Virtuwell software. Depending on what we have available for information or what it is we are trying to accomplish with Virtuwell, would determine which module or modules we would need to use to get the answers we are looking for. For a gas well, in the Sandface Wellhead AOF module, we provide 4 methods to calculate and display a deliverability curve at the wellhead and at the sandface. Here I selected Use Wellhead Flowing Pressure, then entered the current average reservoir pressure with a corresponding standard rate and wellhead flowing pressure to calculate my AOF. In the Gas AOF TPC module, I can either enter the required information to create a deliverability curve, or I can import it from either Virtuwell's reservoir model, or I can import the AOF curve I calculated using the Sandface Wellhead AOF module. Next, I can overlay a tubing performance curve and view my current operating conditions. We notice that the tubing performance curve has a dotted and solid portion. The transition point shows whether we are operating above or below the critical rate required to lift the liquid in this well. We can see that we are currently operating above the critical rate. However, we could also conclude that in the near future, we will probably begin to experience liquid loading issues. We can take a closer look at the critical conditions for my operating point if I go to the Velocities tab and click on the V button for my corresponding tubing performance curve. We can now create multiple tubing performance curves and compare various changes to our configuration. In tubing B, I simply lowered the wellhead operating pressure. We see an immediate increase in gas production and a significant decrease in the critical rate required to lift liquids in this well. Tubing C and D simulate if I were to run a 1.5-inch coil at the original operating pressure and at our new lowered operating pressure. For an oil well, we can see that we have a few options for calculating an oil IPR curve. If we look at the required information for the multiple Vogel method, we first need a current reservoir pressure. If we have a recent buildup in liquid level, the acoustic well sounder module will provide our shut-in sandface pressure. Next, we need to determine the sandface flowing pressure. We can enter our current rate and wellhead flowing pressure information in the wellbore module and calculate the resulting sandface pressure. Then enter our current oil rate and display our IPR curve. We can again create the tubing performance curve of our current conditions, and then what-if scenarios. In this case, for tubing B, we increase the gas-oil ratio to try to simulate additional oil production due to gas injection. And in tubing C, we compare the results of effectively lowering the wellhead pressure. By turning off all of the tubing performance curves and entering a water cut in the composite model, I can see the resulting water, oil, and total liquid curves for this well. By entering a pressure in the column on the right, we see the resulting production rates of oil, gas, and water at that operating pressure, which could be the equivalent of the suction side pressure for a downhole pump. I can once again turn on my tubing performance curves for additional comparison. F.A.S.T's plunger module can be used to model a well currently on a plunger lift system to determine if there is potential to optimize overall production, or to determine if a plunger lift system is an option for continued production from a well that is beginning to experience unstabilized flow or is severely liquid loaded. Required information for the plunger module is accurate current AOF information and additional installation parameters to model a single cycle of a plunger lift system. Our first plot shows a single cycle of how I would expect my plunger system to operate, which includes my casing, tubing, and line pressures, as well as my wellhead and bottom hole gas rates. From the beginning of the cycle, the well begins to unload and the plunger rises to surface. The plunger is then trapped at the wellhead, and the well is free-flowing. The well is shut in, the plunger travels down to bottom, and the well builds back up until the cycle repeats itself. We also provide a nodal plot, which displays the AOF curve we entered for the model, as well as where we would expect the current plunger configuration to operate. For faith that we would be able to repeat the cycle, we require that the casing pressure at the end of the cycle builds up to the casing pressure at the beginning of the cycle. Failure for this to happen will result in an error with instructions of how to correct the model. The operating tab then displays calculated outputs based on our deliverability and installation parameters, such as the required casing pressure to be able to achieve the specified rise velocity, the calculated amount of shut-in time for the casing pressure to build back up to the original casing pressure, our average daily wellhead gas rates and average bottom hole pressure, an expected slug volume for each cycle, and a value for a load factor, which is a rule of thumb value used to determine if the model would be able to provide the necessary amount of energy required to lift the plunger and slug all the way to surface. For additional information or for technical support about using Virtuwell, please don't hesitate to contact F.A.S.T.